Hello, Math 126 fans. Now we're going to talk about partial derivatives and tangent planes. I'm going to try to hit that in this one topic. I'm going to say a few general things, show some visuals, and then we'll do a few problems. If you want, while you're listening here, you might try to do the partial derivatives on that. This is from one of my old exams. It's fall 2018. But first, here we have this function. You should know the name of this. It's it doesn't. I mean, the reason you should know the name is because it was on exam 1. But this is a hyperbolic paraboloid. But students who've taken this course with me know that I never call it that because it's a Pringles chip. If you don't know what Pringles are, go get some. Once you pop, you can't stop. That was their commercial. Anyways, the partial derivatives is a very particular skill. It says when I ask for dz dx, I am saying there's only two variables in the problem, z and x. And y is going to be treated like a constant. So you should know at this point, it should be starting to become second nature, that dz dx is 2x. That means the slope in the x direction. I'll show you some visuals of that in a moment. But it means if you just turned it into a 2D problem, replace y with a number, then this would give you the slope. And I'll show you that in a second. The slope in the y direction does the same thing, but treats x like it's fixed. It's going to be negative 2y, no problem. We do then, unfortunately, have more second derivatives. And I had a great student that I've been working with the last 2 quarters, took Math 125 with me. She said, how do I check my work? It is something you need to get good enough at that you don't have to check. But there is something you can check, this so-called mixed partial. So if you take the derivative of this with respect to x, you get 0. If you take the derivative with respect to y, you get 0. If that doesn't match up, then you know something went wrong. That's Clairaut's theorem. Okay, anyways, with respect to x twice is a 2. With respect to y twice is a 2. This does give us some sense of concavity. The mixed partial is a little harder to visualize, but I will try to do that for you in just a second. So let's look at the Pringles chip, because I think that gives us, we'll talk about that visual in a second. Here's the Pringles chip. Doesn't look like, sometimes we call it a horse's saddle. I don't know, whatever you want to call it, whatever you want to look at it as. I feel like the scale looks funny. Ah, that's what I did wrong. Oh, that looks worse. Well, that looks even weirder. Okay, let's talk about this Pringles chip. So what we're doing is we're fixing something. So let's say we fix y. The moment we fix y, we're turning it into a 2D problem. I'll make this a little bigger. We're looking at that 2D intersection. Let's see, do I have a... And we are going to talk about this slope at a given point. So if I get rid of the surface, you start to realize, oh, I already know how to do that. I just take the derivative. Now, it always is going to mean as x increases, so you have to sort of orient yourself like you're used to. But here I have positive x is as I go to the right, and if you're looking at my mouse there, hopefully I should check these videos. Can you see the mouse? But I think you can. So if you go to the right, we can see the slope is negative there because the value I'm at. Okay, so let's go to a value of positive value of x. So when you get to x equals, well, how about 2? You get to x equals 2, the slope is 4 because we had this formula 2x. That's what that meant right there. Okay, let's put the surface back up there. That's the slope in the x direction. When you're standing at a particular y, let's move y. I don't know, like over here. The slope there is 2. Okay, if you take the second derivative, you're asking yourself, how is the slope changing if you change x? So if you do x twice, the question becomes, how is the slope changing as x increases? So I'm going to go to the negative, and I'd like you to see what happens to the slope. Does the slope get bigger or smaller as I go this way? Bigger, 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 0, positive, bigger, 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 bigger. We call that concave up. And that's how we deduce what this 2 means. This 2 is the second derivative with respect to x, which has this funny notation. And that means it's concave up. I'm saying more here, but this is important. We need to know this. Concave up in the x direction when y is fixed. So very important ideas in measuring things. This one says it's concave down in the y direction, so let's go look at that. And thanks for hearing me. We'll do the homework questions. I just feel like we got to have this baseline of understanding. Okay, so now let's do this. And I just want to use these visuals I've made since you're not taking my course. I think they're awesome. Okay, now let's fix x. I don't know why I did it that way. Let's fix x. Let's make x come back here a little bit. And now we're doing the same thing, but in the other direction. So instead of fixing y, we're fixing x, and we're going to find the slope in that direction. I need to make it bigger. There we go. Let's find the slope in that direction. So I'm going to draw the line in this direction. There it is. Let's orient it so we have positive y is to the right. And so you should see that that has a negative slope. Because if you take a step in the y direction, you go downhill. Okay. In fact, at the particular y and x we're at, the x doesn't matter, but the y does, the slope would be -6 right there, because we saw it was -2y. That's what that is. You can see, once again, as we increase y, now the slope is getting smaller. That's what we mean by concave down. That means our graph looks like a frown. All right, that's what's going on. Okay, so we just did what the first derivative means. It means the slope. We did what the second derivative with respect to the same variable means. If it's positive or negative, it's the same concavity idea as in Calculus 1. So what about that mixed partial? What that is measuring is how does the slope change when you're looking, right now we're looking in the y direction. How does the slope change if I take a slight step to the side? In video games, my son calls that strafing. You're like running to the side while you're running forward. I'm just slightly too old to play video games where you could strafe. I guess we played GoldenEye. It was a Nintendo 64 game, so I strafed a little bit, but anyways, so we're going to step to the side. So right now we're looking in the x direction. We have that slope, and let's step to the side. So instead of increasing y like I was doing a moment ago and we saw it was concave down, I'm going to increase x. You tell me what happens to the slope. You can't because you're not here. What's going on? That's weird. The slope didn't change. That's what the mixed partial is measuring. It measures a little bit how things deviate around the point. Now, if you need a full discussion of that, you have to do something called directional derivatives and the second directional derivative. But it turns out the formula for the second directional derivative, which I think is in 14.6 or 14.7 of your text, involves the partial with respect to x and the partial with respect to y. And there's enough information there that you can make deductions about what's happening around the point. So that's really all you need to know. But the important thing is actually they measured the same thing. Meaning, if we're going the other way, and we're at some x value, and you increase y, it's also 0. So the important thing for us is that they measured the same thing. And so that's what's going on. Okay, that was more than you bargained for. Okay, let's get back to the problem. So if a question says find the tangent plane, that should not scare you. You immediately write this. I find sometimes it's surprising to me when it comes to formulas. I mean, when I was a student, if there was a formula, I was like, okay, I got that question. So there's no reason not to write this. You might say, well, how do I fill it in? Well, you've done quite a few of these homework questions. Let's fill it in. They gave me the x values, 1, and the y value, 1. All right, that wasn't so bad. Now we need 3 numbers. We need the corresponding z value, we need the slope in the x direction, and we need the slope in the y direction. So this is really just a partial derivative question. Now, if you want, you could plug in the 1, 1 right now. I think when I asked this question, it was like in a fall quarter where I wanted to make sure students could compute a few things. This is going to end up being sine of pi, which is 0, log of 1, which is 0, and 4. So it's just 4. So that wasn't too bad. Now, usually in class, students have me do that calculation for them, but let's save ourselves a little bit of time. I'm already too long-winded as it is, but I hope you're getting some out of this. Okay, now let's talk about the partial derivatives. Okay, so we're going to play this game where we're going to switch focus. So first, let's figure out the partial with respect to x. So what I tell students is identify your variables and where they live. And also do all the things you've been learning throughout calculus, which is rewrite things in an ugly way so that calculus is easy to do. Okay, done. Here is your automatic thought process, the way in which anyone can do a partial derivative. We'll get to that question in a second. Anyone can do a partial derivative. It's really just derivatives in general. So when I do the partial with respect to x, sorry, I should have written a y here. When I do the partial with respect to x, I look at this variable, this variable, this variable. Step 1, this is just reviewing your derivative rules. The derivative rules go like this. First, the sums come along for the ride. The sums and differences come along for the ride. That's the sum rule for derivatives from Calculus 1. So basically we have essentially 4 terms. This term, 1. This term, 2. This term, 3. And this term, 4. So we have 4 separate jobs to do. If a term doesn't have an x in it, that means it's a constant term, and the derivative is 0. And right now I'm doing the derivative with respect to x. That means this is also 0. Students can't, it's hard for students to not say 1 over y. The derivative of this is 1 times dz dx, so 1 dz dx. You don't have to write the 1, but you do need to recognize we're differentiating both sides. Okay, and then we're left with this term. Unfortunately, this term has 2 x's in it. When you have a term that has 2 x's in it or is complicated in some way, then you're going to be doing the product, quotient, or chain rule. In this case, it's definitely the product rule, and that's a Calculus 1 idea. So then you start doing the product rule. So this is more just a review of how to take derivatives. This sort of reinforces. So I'm going to do first times the second. Let's do the derivative of the first. And then I'll copy down the second. Whew, that was tiring. We did it. And then these are all zeros, so let's just erase them. And then I need to do the first times the second. And this, I'm teaching the same thing to my business math class and in other classes where you just need to, then you have a new job. I need to take the derivative of that with respect to x and plop it here. This is a chain rule. Take the derivative of the outside. It's going to be cosine. Lovelace law of the c's. If it starts with a c, the derivative is negative. It didn't start with a c. You copy down the inside, pi x, y to the negative 2, times the derivative of the inside with respect to x. So now we're finally here. We're treating x like a variable. Anything sitting next to x is what we call a coefficient. So you're going to copy down the coefficients. I know sometimes it looks funny to have y be a coefficient. And then you're going to take the derivative of x, which is just 1. There you go. So that's a full accounting of how to take the derivative with respect to x. Let's play the game again. So here's the function, x to the 5th, sine pi x, and I have plenty of practice on this on my website. I just wanted to do one video where I just talked about this. Now we're going to shift gears and do the derivative with respect to y. So these are our variables. So now let's analyze now. So we can take the derivative of the left. It's just going to be 1 dz dy. We're going to see that we have 3 terms on this side. Are there any constant terms? Yes, there are. Here. Are there any other constant terms? No. This has a y in it. Are there any coefficients? So kind of the process is, are there any constant terms? Okay, done. Are there any coefficients? Yes, there's a coefficient right here. A coefficient is something that we're treating either a number or treating like a number that's sitting next to a function. So the coefficients and the sums just come along for the ride. Okay. Now we start taking derivatives. The derivative of this is 1 over y. And now we're finally down to this. We're taking the derivative with respect to y. Y is trapped on the inside, so we got to do the chain rule. Copy this down. And then finally the derivative of the inside. These two things are coefficient times the derivative of that, so it's going to be negative 2. For some reason, putting the negative 2 squished in there bothers me, so I'm going to put it out in front. Negative 2 y to the negative 3. Done. You finish this question by plugging in a 1 to both of these. I have that in my notes. This is from my fall 2018 exam. When you plug it in to x, you get negative pi. This is 0, so you get a negative pi here. And when you plug it in for y, you get 2 pi. Yeah, 2 pi plus 1. So this ends up being 2 pi plus 1. But I really want to emphasize the process for how you do partial derivatives. Let's pull up, it's always, if you want to check out my lecture notes, you can see examples of this. I do have, make this a little bigger here. I do have several practice pieces here. So like I find students that struggle with partial derivatives, I just give this in class. And there's examples. And then I have another sheet that has more partial derivative practice, including, more complicated situations, and I review derivatives. Okay, so the main takeaway from all that is it's mostly derivatives we already know. You can use Clause's theorem to sort of check your work. Here it's a pain in the rear to do Clause's theorem. If you took the derivative with respect to y of this and the derivative with respect to x of this, they should be the same. That's going to take quite a bit of time, but if you really wanted to be sure. Okay, one last question. So this sort of scares people because it's combining a few things, but it shouldn't. And again, check out that review sheet if you want. I should have said before I leave this question, whenever I write exam questions now, I always make a visual. So I have visuals for these from when I taught these courses. This is what a tangent plane looks like. Ooh, fun. There's a tangent plane. That example we just did is a terrible function. It looks just disgusting. We can't even graph it very well because it has all these asymptotes. So what do we do if we're trying to approximate it? Well, one method is to find a tangent plane. And these are what the tangent planes look like at various points. We found it when x and y were both 1. So right about here. And this is a very valuable method in any situation because the moment you do that, then, we're going to replace it with this. Now, is it going to be accurate? No, it's only going to be accurate near 1, 1. But we've linearized what's happening. Okay, so let's finish with this one. Consider this surface. We need to compute the partial derivatives. Here we go. So they've given me the x, y, and z. I just need the partial derivatives. So the reason we do this is not because we want to torture you. It's to force you to understand what this notation means. This notation means x is a variable, z is a variable, and y is a constant. So let's break it down from that perspective. So x is a variable, z is a variable, and then we have this 8. I feel like I want to distribute it. I don't know why, but let's do it. xy plus 8. So let's underline the variables. There's a variable here, there's a variable here, there's a variable here. Everything else is a constant. Now let's do our analysis. If I differentiate with respect to x, and I treat y like a constant and z like a variable, what would happen? Well, the derivative of this was going to be 0. This is a coefficient, so it's going to come down. And that's that same analysis. Now, if I just have one x here, I can just start taking the derivative, so it's going to be cosine the inside And now I need to take the derivative of this term. The derivative of x is 1. Y is a coefficient, so there's just going to be a y here. The part that challenged students was this side. I do have two variables here. Two things that are being treated like variables. We think of z as a function of x, and I could spend a lot more time talking about this, but we need to differentiate it. It's like it's trapped inside of a third power, and so the derivative is going to be 3z to the x squared times the derivative of z. But rather than write it that way, we don't write the z of x because we don't need to. So anyways, I'm going to write first times the derivative of the second plus the derivative of the first times the second. So the first is x, the derivative of the second is that 3z squared times z prime, or d. It's better to write dz dx because you need to be clear which variable you're using. The derivative of the first is just 1 z cubed. So that's it. So those questions bother students, but they really are testing your understanding of what is a variable and what is a function. We didn't need to do the product rule here because only one of those was a variable. We did need to do the product here because both were variables. Okay, that's the game. One comment in terms of finishing this problem, I know I'm starting to get into my head there, is at this point you can plug your numbers in, meaning you could plug in a 1 for x here, a 2 for z here, a 2 for z here, a 0 for y, so that side is 0. I would strongly encourage you to do that because this just gives you 12 dz dx plus 8 is 0. So then you can quickly solve for dz dx. Let's play the game again, but let's now do it with respect to y. Okay. Erase, 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 y. So if we're taking the derivative of z with respect to y, how do things change? Let's analyze it. Now the variables are z and y. And so now let's look, are there any constant terms? Yep, that's just going to be 0. Are there any coefficients? There's actually a couple. There's one here and one here. X is a coefficient. It's just a number sitting next to a function. This is a little easier because I don't need to use the product rule anywhere. I just need to do 3z squared dz dy. And then here it's going to be cosine xy. The derivative of y is 1 times x. Done. So that's the point of those sorts of questions. Now, once we have all those things and plug in all the numbers, we can give the tangent plane. It's z minus 2, it's x minus 1, it's y minus 0. I'm getting those from these points. They gave us those. And then the slopes I'm going to get by plugging in. So I'm going to steal this from my notes. This is... this one became negative 2/3, and this one was 2/3. I'm looking at my solutions. This is a winter 2015 exam, if you want to see the full solutions. So sometimes students go, but what about this linear approximation thing? This is the linear approximation. You have nothing new you have to do. So a question that says use this as a linear approximation is saying, I want you to plug in a 1.1 here and a negative 0.2, and then I want you to tell me what z is. Now sometimes we use this notation L of xy, but that shouldn't scare you. We just are saying, well, the z is going to be 2 plus whatever we get out of the rest of this. So I think students don't understand that a question that's about linear approximation is just asking you for the tangent plane. That's it. Okay, so in this question, you're just going to plug this in here, tell me what z is. Done. That's just one of the main applications. So I spent too much time there. I have too much to say. But if you need more practice, the place to go would be here. Now, typically, this is kind of how this goes. You overshot. The 12-3 homework really puts you through the ringer of lots of different partial derivatives. But the hope is by the time you get to 14-7, where you really need them, those problems are a lot tamer. So in practice, you're not doing things as messy as this, but you should probably expect one question where you have to think through things like that. All right, hope that helps.